Hi, this is Tony Northrup for Train Signal, and in this video lesson I'm going to talk about security evaluation and assistance for the SSCP certification exam. So in this lesson we're going to talk about how to check out products that you're buying or thinking about buying to make sure that they meet your security requirements, because you'd be surprised how many products out there are just terrible security-wise. Up first, I'll go over product evaluation. I've discussed this in other lessons, but everything in security is about scales of gray. It's not black and white. There's no product that's insecure or another product that is secure. Okay, well, maybe there are products that are insecure or not secure, but nothing is perfectly secure. Even Fort Knox, the biggest bank in the United States, isn't perfectly secure. Somebody could theoretically get into it. People still have access to it. Anytime you make information accessible to people, you also open up vulnerabilities. So everything is some level of compromise. Just keep that in mind throughout this lesson, because I'm going to be showing you how to nitpick every little product that you see and find every potential security vulnerability. And it doesn't mean that you need to not buy any product that you find any flaw in. They're all going to have some flaw. You just need to find a way to mitigate it or simply accept the additional risk. Now, when evaluating products, don't trust the manufacturer. You can't go to their website and read a product description that they wrote and say, oh, it says it's trustworthy and secure, therefore I trust it. And don't trust anybody who might make a product. So don't trust the manufacturer. Don't trust a salesperson. Don't trust somebody who has an affiliate link to a product. That's a link on a website where they might make, 5 or 10% of the sales for it. Those people all stand to make a profit, and therefore you can't trust them. If somebody's going to make a buck, they're not your friend, they're a vendor. They're trying to make money from you, and you have to be skeptical. It doesn't mean that they're not telling you the right thing or that they're not being honest, but you don't know that because they have motivations that would pull them in the other direction. Throughout this lesson, I'm going to be discussing some certifications that help to show that a particular product has some level of security. I want you to remember that certification doesn't prove security, it just shows compliance with the particular certification requirements. So the certifications will outline a bunch of things that the product needs to do. If it gets certified, it complies. Doesn't mean it meets your requirements, though. The classic structure of an evaluation has these three components. The first is functionality. Does it meet your requirements? Does it do what you need it to do? That's not entirely black and white. When you're evaluating the functionality, typically what you'll do is you'll sit down in a meeting with everybody who's involved, and you'll make a list of needs and wants. Usually you'll sit down in a meeting with every what they call stakeholder. This is everybody who might have a need for the particular product that you're evaluating, and they'll make a list of things that they want and things that they need. And for you to get the product, well, it has to have everything that you need. And if there are multiple products that have everything you need, well, you can start to compare which one has more of the things you want. The effectiveness evaluates how well a product actually works. Sometimes it can meet your technical requirements, but it's just a real pain to use. Or, it might just simply be more expensive to manage. The third component here is assurance. And this basically talks about the quality of the product. Is it reliable and supportable? Can you monitor it? Can you back it up? Can you manage it? If something goes wrong, who do you call? And what are their support guarantees? How quickly do they need to get back to you? What's their track record? If it's a service that you're buying, how many outages have they had? How long have they been offline in the past year? What do their other customers say about them? Now I'm going to go into some standards-based security evaluation criteria. These are mostly government standards that help you evaluate different products, and some products might be certified to meet these particular standards, and if you know that a product is certified, that gives you some sense that it has met a particular level of compliance. The most common of these is the Orange Book standards, less commonly known as Trusted Computer System Evaluation Criteria. It doesn't exactly roll off the tongue, which is why we call it Orange Book instead of TCSEC. These are really old standards, and I can't even believe I'm still discussing them. but you just might see them on the exam. It's a little wink to you there. They were developed in 1967 by the United States Department of Defense. As you can imagine, the Department of Defense, which has a hand in various aspects of the government and military, they have to evaluate a lot of different products to make sure that they meet their security requirements. So it's helpful to them, helpful to any sort of government organization to develop a standards-based process, because in the private sector you can pretty much get smart people together and have them think about a product and make a list. But when you're in the public sector, they really want to make sure that you have well-defined processes, because they need lots of transparency. They need to be able to show the citizens of the country that they're following a particular procedure and not, maybe favoring their friends or giving kickbacks to somebody. So it helps to have these kinds of standards, and that's what the Orange Book is. Anyway, the Orange Book is 46 years now. It's older than me, and I'm old. So how relevant is it to computing? Nothing of our computing infrastructure today is much like it was in 1967 at all. So maybe it's not that relevant, but it's still important to understand, because these standards still come up. And companies like Microsoft are still getting some products evaluated and certified with the Orange Book, because it is still important to some military and government organizations. The Orange Book describes 4 levels of security: A, B, C, and D. A being verified protection. This is the highest level of security, and it's almost inachievable. I don't know of anything that has the A level of security. The B level of security is mandatory protection, and then within the B level, you get like a B1, a B2, or B3. These are almost like school grades. Like a B1 would be a B plus, and a B2 would just be a B, and a B3 would be a B minus. So think of it that way. Discretionary protection comes in 2 levels, C1 or C2. D means that a particular product was evaluated for the Orange Book certifications and it failed. It basically didn't pass. The Red Book. Oh, this is a super modern update to the Orange Book, but you don't even hear about it very much. It was developed in 1987, so that's how fresh that is. Compared to the Orange Book, it's a baby. It basically adds networking to the Orange Book. Yes, the Orange Book was developed really before networking was in any sort of common use, so they had to write a separate book 20 years later to add some networking capabilities to it. Anyway, so I want you to remember this distinction between the Orange Book and the Red Book. The Orange Book handles standalone systems, like a computer that's not plugged into the network. Believe it or not, people do sometimes use computers that aren't plugged into the internet. The Red Book handles computers that are connected to other networking devices. So it extends it to cover things like communications integrity, verifying that packets haven't been modified in the way, denial of service protection, hardening to prevent compromise. So the Orange Book and the Red Book were developed by the United States Department of Defense. And believe it or not, there are other countries in the world. There's a few countries in Europe, in fact, and they have government and security needs too. Maybe they didn't want to use these super outdated American standards, so they developed the Information Security Evaluation Criteria, often called ITSEC. It's like the European Orange Book, and it was largely based on the Orange Book. I mean, it's not identical, but certainly they looked at the work that had been done for the Orange and Red Books when they evaluated it. Here are some differences that you'll see in this table here. The Orange Book, as you saw, rates things like A, B, C, D. The ITSEC rates separate attributes in different ways, and we'll see those different attributes on the next slides. The Orange Book is very rigid. It's pretty much like you get one of those grade letters or you get a D. ITSEC is much more flexible, and it can be adapted to different types of products much better. The Orange Book pretty much just addresses confidentiality, because that's where the security world was back in 1967. They were just thinking about code breaking and cryptography and keeping data secure. In 1991, we'd kind of expanded the definition of security to also include integrity and availability. So ITSEC reflects that sort of shift that happened in the security community across those 24 years. The Orange Book, of course, is designed for standalone systems. ITSEC, like the Red Book, is designed for both standalone and network systems. ITSEC has a variety of different functional requirements. And this is what I was referring to when I said that ITSEC had more flexible criteria than the Orange Book. You can see all these different criteria which are labeled with these F numbers: identification, authentication, auditing, resource utilization, trusted paths and channels, user data protection, security management, product access, communications, privacy, protection of the product's security functions, and cryptographic support. And these are assurance requirements. And if you remember in the beginning of this lesson, I talked about the 3 phases of the evaluation, and 2 of them were functionality and assurance. Well, the previous slide was covering the functionality, and this slide is covering the assurance. So this is more about being able to support the product and making sure that the product itself was developed using strong security techniques. So these 7 different levels are guidance documents and manuals, configuration management, vulnerability assessment, delivery and operation, lifecycle support, assurance maintenance, and development. Here's another international organization that made similar standards, and they just kind of blended together the best of what you've seen so far, and it is ISO, the International Organization for Standardization. And if I can have a quick sidebar here, ISO is not ISO, even though it sure looks like it. Now notice the name of the organization is International Organization for Standardization. If you were to make an acronym out of that, it would be IOS. But it's called ISO because it's not actually an acronym. This is unbelievably confusing. And everybody messes this up, and if you say ISO, a bunch of people will correct you and get mad at you and think you don't know what you're talking about. If you say ISO, a bunch of people will get mad at you and correct you and say you don't know what you're talking about. So it's kind of hard to win. But I've done some research into it, and the proper name for the organization is ISO. You don't spell out the letters. ISO is a shortened form of the Greek word isos, which is I-S-O-S, though it had different letters in the original Greek alphabet. And the interesting story behind this is that ISO is, of course, an international organization. And while in English it's the International Organization for Standardization, in French the words are slightly different, in Spanish the words are different, and they'll come in a different sequence. So there was no one acronym that they could use that would be correct in all different languages. And they're so concerned about being internationally friendly and not favoring one language over another that they didn't want to choose a language-specific acronym to be identified by. Therefore, they picked this old Greek word that means equal. ISOs just means equality. And you'd see it in lots of words like isometric. So that's my story about ISO, the organization. And if somebody says, let's talk about the ISO common criteria, you can say, funny little story, it's actually ISO, it's not an acronym, it's based on a Greek word. So anyway, getting back to the common criteria, they took a look at all the standards that we've covered so far and made a more modern and international version of it called Common Criteria, or CC. And nowadays the Common Criteria is the most commonly used, though I think you probably hear about the Orange Book more than anything else. The Common Criteria uses protection profiles called PPs. So CCPPs, I guess. And these protection profiles can be extended to a lot of different technologies because the Common Criteria is much more flexible than the other standards that we've covered. But some of them are operating systems, the public key infrastructure, which manages certificates for asymmetric cryptography and digital signatures and such, switches and routers, which are part of your network infrastructure, biometrics, which are retina scanners and fingerprint scanners that you might use to authenticate yourself, firewalls, which protect networks and hosts from unwanted network traffic, wireless local area networks, WLANs, which are, Wi-Fi, virtual private networks, which allow you to connect privately across the internet to an intranet, and of course smart cards, just another form of something you have authentication. Now the Common Criteria uses evaluation assurance levels, and these will exist for all of the different protection profiles that you just saw and any new protection profiles that might exist. And basically EAL1 is the worst grade you can get, and EAL7 is the best grade you can get. I don't know why they didn't go to 10 or, give it grade letters, which would have made more sense to people, but it's difficult to remember this. But EAL1 is the worst and EAL7 is the best. EAL1 just means it's functionally tested, which means, yes, it does what it's supposed to do. And, it means it failed, basically. It didn't completely fail. It does what it says, but they weren't able to verify the security of it in any strong way. So if you see an EAL1, that's a bad sign, right? And each of these adds a couple of different features. EAL2 is structurally tested, EAL3 methodically tested and checked, EAL4 methodically designed, tested, and reviewed. So notice that this is just saying that the design overall is secure. EAL5, semi-formally designed and tested, and then semi-formally verified, designed, and tested, EAL6, and finally formally verified, designed, and tested. And so what do these mean? Well, they don't mean anything unless you understand the protection profile itself. So if you're in a particular industry, you'll probably get to know the common criteria and how it works, as well as a specific protection profile, say, for operating systems. And only once you understand that criteria and what it takes to meet each of these different levels can you really assess it. In other words, if you see some product and it says it's CCEAL5, well, I guess it's a good sign. It means they went through some effort. But until you examine that protection profile and figure out what it actually means, it doesn't actually mean anything to you. So take it with a grain of salt. One of the products most commonly evaluated by security guys like myself are security cameras. And they're also one of the most complex things because, well, they're quite subject to attack. You see this in every spy movie. Either they'll shoot the security camera with their gun, or they'll take like a spray paint can and spray it over it, or, you know, they're watching it move back and forth and they're like hiding in the shadows and dodging out of view. And security cameras really are important because you can put a security camera somewhere and monitor a particular location without assigning a physical person there. So basically they allow a single security guard to monitor a much larger area. Security cameras are incredibly complex to pick, and if you pick the wrong one, it might not meet your requirements entirely. So I just wanted to cover some of the more common acronyms and standards that are used for evaluating security cameras because it gets really confusing the first few times you do it. The term CCTV just means closed-circuit television. So closed-circuit television harkens back to some electrical engineering thing, but if you think about closed-circuit television, what it is it's security cameras and televisions, monitors, that watch those security cameras, and they don't go out into the rest of the world. They're all in a building, and so that's what they mean by closed circuits. The camera and the monitor are all within a single facility, and it's not being broadcast anywhere. But with that said, I've never heard the term open circuit television used, but just be familiar with it. If you see the acronym PTZ, that means pan, tilt, and zoom. And what this is useful for is that if somebody is actively monitoring a security camera and they see something fishy, well, they can move the camera over there and maybe zoom in a little bit. And this accomplishes a couple of things. And obviously it might let them see a little bit more detail and investigate a situation without physically moving to it, which would take them some time. But the simple act of moving a visible camera at somebody who's being suspicious, 9 times out of 10, that's going to make them stop being suspicious, right? They're going to stop. So imagine if you're just a security guard at a retail store and you see somebody who might be shoplifting and they hear a camera turning and they see it pointing right at them. They're probably going to stop their shoplifting and just run out of the store as fast as they can, right? So in a way, being able to physically control a camera like this can actually prevent people from doing stuff. If you're monitoring the outside of a data center and you think somebody's going to vandalize it or try to break in, and again, they see these cameras pointing and turning at them, they're going to know they're being watched, and they're going to know they're getting busted if they don't get out of there. So pan tilt zoom cameras can actually be really useful. IR is infrared. That gives you night vision, and the way these cameras work is they have, basically, they're like flashlights attached to the camera themselves, like as if you had a spotlight on the camera, except it's using light that's outside of our visible spectrum, as well as a sensor that can receive light signals that are outside of our visible spectrum. So you can illuminate the area within, usually it's like 50 feet or so. Just like any flashlight, it has a limit to its range. And if there's a human being there, they won't be able to see the infrared light coming in. So it's not disturbing anything. I guess some animals could see it. Snakes could certainly be able to see it. And somebody might be able to perceive it if they brought along something that could monitor infrared light. But infrared basically allows you to see at night with your cameras. You also see IP ratings, which I'll discuss more in the next slide, and that just means that they have some level of waterproofing. You don't need waterproofing if you're going to be putting the camera inside. If you're going to be putting the camera outside, you definitely need some waterproofing. If you're putting it on a lighthouse where there's going to be waves slapping against it, you're going to need even more waterproofing. TVL stands for the television lines of resolution. So if you think about TVs nowadays, the standard definition TV is 480 lines of resolution, and then HD could be 720 or 1080. Well, with these video cameras, what they're actually talking about is how many different lines can it resolve. So it's a factor of the quality of video that it's putting out, but also the quality of the optics and the video sensor. And basically higher is better. It lets you see more detail, but you might not even need that much detail. It just depends what you're monitoring. IP cameras, of course, IP stands for Internet Protocol, which is the networking protocol that the Internet is based on. And IP cameras can be connected to a network, so you can monitor them with a computer. Sometimes they're wired and they need a wired Ethernet connection, and sometimes they're wireless, so they can just connect to your Wi-Fi and you don't have to worry about getting a cable to them. The alternate to an IP camera is just a traditional video camera, which requires usually a coaxial cable to be plugged into it. Sometimes they have specialized cables too, but nowadays I'm all about the IP cameras. I want everything connected to the network. And if it is an IP camera, you'll see the different video codecs that it uses. And the three most common would be H.264, MPEG, and then MJPEG. And whatever software you use to watch your IP cameras, to monitor them in real time or to record them, will need to support these same video codecs. But for the most part, all these video codecs are widely accepted, so I don't really see any compatibility problems in the real world. Here are those different waterproof standards that I was talking about. IP66 is equivalent to another standard called NEMA, and so IP66 is equivalent to NEMA 4. And this is basically the lowest level of waterproofing, but it's going to be fine for most everybody. That means it's water resistant and weatherproof, and they have to go through some testing of the design to make sure that these cameras withstand a certain amount of spray being sprayed right at them. IP67, which is roughly equivalent to NEMA 6, is a step stronger waterproofing than IP66. That means it's waterproof rather than water resistant, and basically they have to submerge it briefly in water, not to deep depths or anything. And IP68, which is equivalent to NEMA 6P, adds some dust proofing in there, so it's slightly different from waterproofing, but it also helps keep the dust out, which is good if it's in an industrial facility. Imagine if it's a lumber mill and wood is being sawed all day. You don't want dust getting in near the camera sensor. Now let's talk about data flow management, which is the process data follows to get from whatever database it's stored in to whatever user wants to consume it. First, what is data flow? Well, data moves. It moves around a lot. We store it in databases usually, but if you're going to get to it really frequently, the data moves from a database to the web server and then through something that processes it, such as JavaScript, and finally it's displayed in a web browser. So if you think about it, every step of this path is something you need to evaluate for security, because the vulnerability in any one of these components could compromise your data. So you want to make sure that the data stays confidential in every single step and that the integrity is also protected. So there needs to be some sort of checksum, because you want to make sure that the data isn't being changed, modified, or viewed along any part of the process. You also need to verify the availability. So in security and design in general, there's a concept called single point of failure. And that means that if one single component fails, well, the whole application fails. So you might have this complex architecture with a database cluster and geographic distribution, but if all the data is being accessed through a single web server and that web server crashes, well, your availability is gone. So you'd also want to set up multiple web servers and probably some load distribution, and then you'd want to make sure that your network equipment was configured redundantly so that there was no single point of failure if you required that level of availability. I also want to talk about how the data gets put into that original database. Somebody's typing it or scanning it or taking a picture of it or reading it aloud. However it gets in, that's a potential vulnerability. Anytime you let somebody update the data, that's a potential vulnerability. And it might be through a web interface, it might be through a web services interface, or it could be through the database directly. You need to evaluate every point of input for security concerns. Now I'd like to talk about how to assess data flow confidentiality when you have to store a password. While many applications use a single sign-on infrastructure where you can authenticate users based on an existing infrastructure that you have, such as an Active Directory domain, well, many applications require their own separate login. And if an application requires you to enter in a username and password for everybody who's logging in, then you need to evaluate how it's storing those passwords, because this is a common problem. I want you to check for how the passwords are stored. You don't want them to store the password. No, you want them to store a hash of the password. A hash is non-reversible encryption. So if I type in my password, it's probably my dog's name or my birthday or something like that, right? Well, I don't want to ever see that in a database. I want them to run it through some MD4 hashing algorithm or some other hashing algorithm and output this usually shorter and non-reversible, what looks like random garbage. Then whenever somebody logs in, the application is going to accept that raw text password and perform the same hashing algorithm on it. Then it's going to compare the hash in the database to the hash of the password they just typed in. This allows you to authenticate people and verify their password without actually storing their password. And that means that somebody can get into the database and it's much harder for them to find out people's original passwords. Salt makes these hashed passwords unique. And basically they add a single phrase or sequence to somebody's password. So if I type in my dog's name as my password, Sandy, the application wouldn't just hash Sandy, it would hash Sandy and then my salt. Usually it's not literally the words my salt, but it'll be some randomly generated sequence of letters and numbers that's specific to that individual application or system. And then whenever I go to log in again, well, it'll add that same phrase back to the password. Now, it doesn't sound like it would be that secure, right? Because this static salt needs to be stored in the application itself, and the same salt needs to be used on every single password in the system pretty much. But it does help security, because even though it's stored statically in the system, somebody would have to hack into the system to figure out the salt. And even once they got that salt, even if you made that salt public, for somebody to hack the password database and figure out the original passwords, they would still have to perform the hashing calculations with the salt for every single password in a password database, and then use that to look it up. So they wouldn't be able to use a pre-existing rainbow table. They'd have to generate their own. And that could take a long time, because these passwords databases tend to have millions of passwords in them, and performing the hashing algorithm can take a while. So by adding a salt to a password hash, you really raise the bar for somebody who's going to hack the password database. And as I mentioned earlier, the number one thing you want to see in a system that uses passwords is, can they use your existing single sign-on system rather than requiring them to store their own passwords? Because every new password you make the users memorize, well, that's another opportunity for them to forget their password or use some super cheesy password like their dog's name, or write their password on a post-it note. The fewer passwords your users have, the more secure they are in general. When you think about data flow confidentiality, you need to think about how the data is encrypted, and you need to make sure it's encrypted from front to back, because I see mistakes happening like this all the time. First, it needs to be encrypted on whatever client it's stored on, and that doesn't mean just on the hard drive, but it's helpful if it's actually encrypted in the memory too, because if, say, a PC is displaying confidential data on the screen, and that PC has a rootkit, well, that rootkit can go and read that data in raw form from the application. That's scary, right? So modern best practices for application developers to store data encrypted in the memory, not just when it's on the disk, but of course also when it's on the disk. And this is a front-end application server. Often this is a web server or it's a web services server. And what this does is it takes data from the database here and just basically formats it in the format that the client here needs. So it's kind of a middleman, and it doesn't do a whole lot of processing, though it often has business logic built into it. And because it's processing the data, because it's accepting the data and maybe even storing it temporarily, it's got to be encrypted. So you need to check it out. And as I mentioned, this third component here is the database, and this pretty obviously needs to be encrypted, right? But it doesn't hurt to verify go ahead and just manually poke into the tables and make sure that everything is clean. If you can see any confidential data when you're browsing the tables, well, it's not encrypted. If it looks like gibberish, that's a good sign. And this fourth component here is the backups. And this is just a classic mistake that I see time and time again. People don't encrypt their backups. And then guess what? If a hacker wants to get all your data, all they have to do is get into your backup system. People always forget about the backup. So make sure that your backup system meets the highest security requirements of any system that is backing up. Another way to assess data flow is the integrity of the content. You can ask yourself, can the data be modified? If the data is modified somewhere between the database and the front-end client where the user consumes it, well, it might as well be modified on the database, right? You're still going to be misleading the user. So you need this integrity integrated throughout the entire data flow. You must protect integrity with hashes, which I discussed in the context of passwords, checksums, which allow the front-end interface to basically perform a cryptographic calculation on the data and make sure that it hasn't been modified since it left the source. Digital signatures, which also use cryptography and asymmetric keys to make sure that data hasn't been modified since it was originally signed off, and you can verify that the signature itself is genuine. If you're concerned about data integrity, which you should be, you also need to make sure that every application enforces some sort of auditing. Auditing tells you who modified data, when, and where they did it. Any serious application that transmits data includes features to enforce data flow integrity. Windows Update does this, of course, because imagine if you could modify a Windows Update. Well, you could put a piece of malware in a service pack or a smaller update and distribute it to every system in the organization. So Windows Update uses these digital signatures and checksums as well as forms of auditing to ensure that updates are genuine and haven't been modified since they left Microsoft. Even BitTorrent, which is a peer-to-peer file transfer protocol, it's commonly abused for piracy and intellectual property like movies and such. But it's not all bad. It's also used for legitimately transferring software and files, and it also includes the ability to verify that files have not been modified since they were originally created, because of course it's a peer-to-peer client, right? So anybody who has access to it could theoretically modify the data. You need some way to make sure that the integrity hasn't been compromised, and BitTorrent includes that feature. Another aspect of data flow integrity is authentication. You need to make sure that every part of the process is genuine. Otherwise, you might be looking at a man-in-the-middle attack. If somebody can inject themselves between the web server and the client, or between the database server and the web server, well, they can modify the data, they could read all of the data. So you need to make sure that every step of the process is a genuine system. There are lots of different ways to do this. You know how users are authenticated because you type a username and password 20 times a day probably, right? Computers can be authenticated too, using systems like IPsec, which can authenticate any two computers in an intranet. Basically, you have to manage the same computers. Or HTTPS, which is the secure version of HTTP. HTTP is the protocol that web browsers and web servers use to talk to each other. So HTTPS basically just verifies that the server itself really does have the host name that you attempted to contact. So if you type https://trainsignal.com, well, it'll contact the server and say, hey, do you have a certificate for the name trainsignal.com? And if it has a certificate with a different name, well, it'll show you some sort of error. So in that way, HTTPS allows you to authenticate servers. When you think about the data flow vulnerabilities, you need to assess the weakest link along the way, whether it's for integrity or availability or confidentiality. You also need to assess the different attack surfaces. So in this diagram you see here, in theory, any of these different components could be attacked directly and perhaps in dozens of different ways. Often the client is going to be the weakest link here, since users tend to own it and they might be forgetting it in the airport or leaving it unprotected in their car, who knows. But you need to evaluate this as well as every other component. And if there is a successful compromise, you need to make sure that it stays contained, that a compromise on the web server won't get spread to the database server or to the backups or to the front-end client. This is actually more common than you might think, especially with web servers. Web servers get hacked, and the hacker or the malware will modify the web server files to create a type of malware that could be spread through JavaScript or web pages to the client. So often exploits are not at all contained and can spread pretty quickly. You need to think about how to contain something if the worst case scenario really does happen. Now I'll talk a little bit about assessing code vulnerabilities through the process of testing. Now, I've been a software developer for longer than I care to remember, and so I'm intimately familiar with the different processes that software developers use to make sure that the code they're writing is as secure as it can be. And here are some of the secure coding best practices. The first is code review, and that means that one developer writes a bunch of code for a program, and then their peers have to review it and look at it. And you know what? Your peers are usually jerks, and they're nitpicky developers, so they're going to be like, you know what, you need to use a typed variable here instead of an untyped variable, or, hey, you didn't check this for SQL injection attacks, what are you doing? Anyway, the code review process helps make sure that people introduce as few security vulnerabilities as possible, and it's not perfect. But it improves things, right? Like I said, security is about gray area, so it makes things better, but not perfect. The code signing process is the process where a manager typically will say, okay, this code has been properly reviewed. I feel it's as secure as we can make it right now. I'm going to apply this digital signature that nobody else has, and then people will only run code that has been signed. You might also think about open source. Now, a lot of people consider open source to be more secure because if it's open source, well, that means that the source code itself is released for public consumption, and you can sit there and review all the code as if you were another developer. And if you spot a part of an application where they didn't sanitize the input properly, you could go in and fix it yourself, or you could contact the developer and say, hey, maybe you could check up on this. The alternative is closed source software. With closed source, you don't get to review the source code. So a classic example here is Microsoft Windows versus Linux. Windows is closed source in that you can't go look at the source code for Windows. Linux is open source typically, which means you can go look at the source code. And is one more secure than the other? I don't believe there's a significant security difference because they both have problems. And in the real world, they both get hacked. Lots and lots and lots. So I don't necessarily think there's a huge advantage to open source, but some people do, so I wanted you to be aware of it. You should also make sure that any application is designed to be secure by default, which means that when you install it, all the security features are turned on. As application developers, we learned this probably 10 years ago, really. And we learned that people just accept all the defaults. So if you make an application and you build a bunch of security features in, but they're a little bit inconvenient, so you don't turn them on by default, well, guess what? Nobody uses them. And then when they get hacked, you can be like, well, but you were supposed to turn the firewall on. Well, that's the way things used to work. Now the way things work are when you install Windows, the firewall is on by default. And if you're smart and you don't need the firewall, you can manually go in and turn it off. Anyway, for whatever application you pick, make sure that it's secure by default or that you can change the defaults to make it secure by default. I just want to cover some terms for code testing so that you're familiar with them just in case you see them on the exam. The first is intrusion testing, which means somebody takes your application and tries to break into it. The next is stress testing, and stress testing hits an application hard with thousands or hundreds of thousands of requests and sees how it handles high amounts of stress. This tests availability, making sure that it stays online. It also tests scalability to determine just how many requests per second an application can handle. Every application fails at some point, no matter how big and powerful the system is. You just need to determine what your organization needs and then test the application up to that point and maybe a little bit beyond. White box testing means that you have the opportunity to see the code and create specific tests to try and exploit different functions within the code. To really understand this, you'd have to be a developer, but I want you to remember that white box testing means you have access to the code and you can design tests specifically for how the developers built the application. On the other hand, black box testing, you don't have access to the code. It's like closed source. So your only chance to test the application is to put user input in and watch output come out. Gray box testing is somewhere in between where you have a little bit of insight but not complete access to the source code. So let's talk a little bit more about how to assess the availability of an application. Ideally, an application would stay up 24 hours a day, 365 days a year for eternity. And that's not possible at all. Instead, we talk about availability in a series of nines. You say it has 5 nines of availability, which means it's 99.999% available. Or sometimes it's 3 nines, 99.9% available, and you go higher and higher depending on how important the system is. So you need to determine how available you need it to be. Every system has to be updated at some point, right? And you have to accommodate for hardware failures and just glitches, somebody who plugs a network adapter into the wrong port or whatever. Stuff happens, things go offline, it's pretty much unavoidable. So part of availability is determining how much you need it to be up and will the system meet that requirement. You need to determine what the max load of it is, which is the scalability, which you can do through load testing. When the system goes offline, does it fail gracefully? And by gracefully, I mean, does it give some sort of friendly error message to the user saying, sorry, the system's offline now, please check again in a few minutes? Or does it fail miserably? And sometimes when applications fail, they'll actually go through and destroy the last few transactions. So you need to make sure that transactions inside the database are rolled back cleanly, that data isn't corrupted, that somebody is notified when the system goes offline. The bottleneck is the aspect of the system that throttles the overall performance. So when you're doing load testing, you'll notice that one particular component fails first. For example, it could be that the web server is running at 2% utilization, but the database server is at 100%, and the database server is what's slowing down the entire process. In that case, the database is the bottleneck. Sometimes it might be the network itself. If you have a gigabit connection to the web server and somehow you forgot that you had a 10 megabit, a very slow connection between the web server and the database server, well, you're not going to be able to use that gigabit connection properly because the data is moving across that 10 megabit connection. In that case, the slow network is the bottleneck. If a system doesn't meet your scalability requirements, or if you think that your business is going to grow and you're going to need to scale it up higher, how do you scale it up? And how high can you scale it? Just a question you need to answer to make sure it'll work in the future. You also need to check out the single points of failure in the system, which I discussed a little bit earlier. But make sure you evaluate the computers and the networking equipment and the connections to the internet and how users access the front-end user interface. How do you monitor the system to make sure that it's online and that it's performing fast enough to be usable by users? And will it survive a denial of service attack, or is it ridiculously easy to take offline? Now, this isn't really a yes or no question because some denial of service attack will take any system offline if the attacker is determined enough and they have enough resources. So you need to decide, well, how long is it going to be offline in the event of a denial of service attack? How can I respond to a denial of service attack? And does this meet my requirements? And when the worst happens, when everything fails, what's the recovery process? How do you pull it from a backup? How do you replace the hardware? These are all aspects that you need to think of when you are evaluating a system. You can test all of this using several different types of tests. Stress testing, also known as stability testing. Performance testing. Well, stress testing tests the maximum load that a system can take. Performance testing tests how quickly the responses come back. So performance testing is more a test of latency. In other words, the web server serves a new page in 0.1 seconds, 100 milliseconds, or the database server is taking only 10 milliseconds to respond to a query. That's performance testing. Duration testing is making sure that a system performs well over time. So you don't push it past its peak load, which you would normally do in stress testing. With duration testing, you'll push it near its peak load and just keep hitting it with requests and make sure that nothing breaks. Duration testing will find memory leaks and it will fill up the hard drive if something is storing a ton of temporary data. It will overheat your computers if they're not cooled properly. That's the purpose of duration testing. And finally, a fire drill simulates what would happen if the application had a critical failure. It's easy to do a fire drill. Just unplug the web server or unplug the database server. Helps to give people warning. Maybe do it after hours. But you unplug it and then you just wait to see what happens. The people monitoring it, well, an alarm should go off and they should call somebody and go check out the physical web server and get that thing plugged back in. Or if you yank a hard drive out of a RAID system and cause the drive to fail, well, they should detect that failure, they should determine what it is, they should go get a replacement hard drive and put it in, they should restore it from the backup if they need to. These are fire drills. They simulate a total failure, and then you wait and watch and make sure that all the personnel involved are able to restore it correctly. I also want to talk about a couple of specific types of attacks that are really common. The first is a SQL injection attack, and if you're a developer or if you've taken a CS class in college, you can probably read this. But the code I've put here is code that I've written, which simply opens up a connection to a database. So you can see the user has provided some input and it's been stored in a variable called ID here. And then the code is creating a string here called SQL string that has a SQL query. Select has shipped from orders where ID equals and then the ID here. This is bad because this code is vulnerable to a SQL injection attack, and here's why. Because it's taking the user input and treating it as a string, and it's putting it directly into the query. So the ID here is probably a number, like a number 1, 2, 3, 4, but it's treating it like a string, which means the user could put in something that wasn't a number, like perhaps an attack. So imagine that this is what the user put in as their user input. They put in a valid number, and then they put in a apostrophe here, which closes the user input, and then they put in another SQL command, drop table customers. What will happen is that the SQL injection attack will create this little query and send it to the database server. It'll perform a select query here, and then it will perform another query here, drop table customers. And what will happen is the database server will dutifully perform the SQL query and return any items that have been shipped with this particular ID, and then it will delete the customers table and cause the entire application to fail. And a SQL injection attack is ridiculously common, happens all the time, just something you should be aware of. If you're looking at code, make sure that the code developers have taken this into account. Another type of attack is the cross-site scripting attack, also known as an XSS attack. And any web application that accepts and then displays user input can be vulnerable to an XSS attack. And all the application developer needs to do is to make sure that user input is sanitized, otherwise known as HTMLified. Imagine that you just have a comments form on a page. What somebody could do is type in hi, which would be a common if useless comment, and then they put in this little bit of HTML code here. And if you know HTML, you'll know that this is displaying an image, but it's basically 1 pixel image, and the source of the image is a different website. Well, if the web application accepts this comment and displays it on the web page exactly as shown, then everybody who visits that web page later will be retrieving this counter.aspx page from a different web server. And whoever owns attacker.contoso.com would then have the IP address of everybody who visited that page. And in fact, their web browser would be displaying a page from that attacker. So if that web page, counter.aspx, happened to have some malicious JavaScript code on it, well, everybody who visited the original page that was just displaying this seemingly innocuous comment would be getting their computer hacked. And this happens a lot. And I have a confession to make. It's happened to me, because I've been a web developer since the web started, like the mid-90s. And you know what? Everybody's made the mistake, and I did too. And my website got hacked. Fortunately for me, it was just somebody putting up spam links. I don't know what they were trying to sell, but nobody got hacked as a result of visiting my site, and I fixed the problem as soon as I discovered it. And I've never made that mistake again. But not everybody's been so fortunate, and in fact, XSS attacks have cost users visiting the websites of these developers who made the security coding mistake. It's cost those users a lot because they often get their own computers hacked, which causes the malware to spread even farther. This is Tony Northrup for Train Signal, and thanks so much for watching this video lesson.